So start with finding bleeder current through the bleeder resistor. So that begs the question, which one of these is the bleeder resistor? And to help you out with this, yes, you called it out correctly. It is in fact R3. The rule of thumb here is this. Bleeder resistor is the last resistor of the voltage divider string. What is string? A nickname for it. String. String versus bank. String implies what type of circuitry? Yeah, string implies series, so S for string, S for series, whereas bank implies what type of circuit? Parallel. So we're talking about the last resistor of the voltage divider string connected to the last R load to ground, GND. How about that? So as you look at this, we identify this leader resistor equals R3. Are we good with that? Oops, 3. Come on, Co. 3. R3. Question? Are we good?
I was just having fun.
Oh, okay. Yeah, R3, R23. Yeah. Anyway, so we identify this as the bleeder resistor as R3. R3 is a bleeder resistor can't be any of the other ones because they're not connected to ground. Number one's not connected to ground. Number two is not connected to ground. You have two loads. The loads are identified as a 50 volt, 5 milliampere load for the first load, and the second load is a 10 volt, 10 milliampere load. So the last resistor of the series group, R1, 2, and 3, that goes to ground is R3. So how do we determine, now that you've determined the bleeder resistor, how do you determine the bleeder current?
10% of the total.
So bleeder current equals 10% of what? Total load current. 10% of the total load current. Do you have a load current specified for the first load? 5 milliamps. Do you have a load specified for the second load? A second current for the second load? 10 milliamps. So what is my total load current in this particular case?
15.
Okay, so this is equal to 15 milliamps. And 10% would be divided by 10, yes? And oops, 10, which would be equal to 1.5 milliamps. Is that correct? The 10% of 15, move the decimal place one place over, you got 1.5 milliamps. Yep. And so that being said, from here, you can set up everything you need by way of a simple VIR chart. And so that's what I'm going to attempt to do now. Let me move this guy up here. And okay, I'm going to detach this for a moment. And now draw. All right, so I'm going to set up a V, I, and an R column header. And I have 3 series resistors and 2 load resistors, right? So that means I'm going to have a certain number of rows. So R1, R2, R3, RL1 for the first load resistor, RL2 for the second load resistor, and we have a total in here. Scoosh this up a little bit. Total. Okay, so if you were asked to fill in this VIR table, you would be able to answer all the blanks that are part of the question set. So we can always rely on VIR for our analysis. So what do we know that we can fill in? What are the knowns? I have a voltage source, yes? I'm going to write that in. So we have 100 volts, goes right there. What else is known?
The loads.
The loads, yeah, we know some information on the loads. So the first load is the 50 volt, 5 milliamp, yes? So I'm going to write down 50 volts and 5 milliamps. What else do we know? We know the second load. Yes, the second load is specified as 10 volts and 10 milliamps. Okay. We were given 5 pieces of facts. We fill in 5 pieces. All the pieces that we are given filled in where it is appropriate. So far, so good? Okay, we just determined bleeder current. Where's bleeder current supposed to go? R3's current, yes? Because we said bleeder resistor was R3, and the bleeder current's going to be 1.5 milliamps. I'm going to write that down here, 1.5 milliamps. So far, so good. So far, we don't have any resistors. We don't need any resistors just yet. For this exercise, resistors will probably be the last thing we fill in, because in order to calculate resistance, we're going to use our friend Ohm's law, yes? So here's your Ohm's law. So you have a V, you have an I, and you have an R. So in order for us to find the R, we need a V over I. So as long as we fill in all of the currents and all of the voltages, we can easily calculate the resistances. Okay, so where do I start? How do I approach this? I have 5 givens and I just determined bleeder current. What am I going to do with this?
Figure out the rest of the currents.
Figure out the rest of the currents. Because the key to solving voltage dividers, write this down, key to solving loaded VD circuits is current analysis. That's your key. If you can do your currents, the world is open to you. So let's go ahead and solve our currents. And let's go ahead and use the electron current, because the electron current flows from which side of the source?
Negative.
It flows from the negative side of the source. So electron current's got to flow down, yes? It flows down and it hits the symbol. What's the symbol at the bottom of the source?
Ground.
It's ground. So does it die there, or does something interesting happen with current? The current, yes, comes over here and flows up this resistor as well as up through this load. And let me magnify this here. And as we magnify this right here, we have 1.5 milliamps, 1.5 milliamps that flows through R3. And we know the current through the load as being 10 milliamps, yes? You have 10 milliamps. So you have 1.5 milliamps coming up to node, and I'm going to label these nodes. I'm going to label this one A and label this one B. So flowing into node B through R3, I have 1.5 milliamps. Flowing into node B, I have another 10 milliamps. What happens when these two currents come to node B? They will join, they will combine, and they will combine to flow through R2, is that right? So how much is combining? Yeah, 1.5 milliamps flowing up through R3, 10 milliamps flowing through the RL2. So they combine to give you how much current flowing through R2? So it looks like 11.5 milliamps, yes? Okay. So let's go ahead and do that. So we have 11.5 milliamps flowing through here. Is everybody okay with the current through R2?
Yeah.
Okay. Now, do I have another current flowing up from ground here through this load? How much current is flowing up through this load? It's specified as what? 5 milliamps, yeah? So I've got 5 milliamps through, and let's call this particular guy RL1. Let's call this one RL2. So through RL1, I've got 5 milliamps. What happens when this 5 milliamps flows into node A and the 11.5 milliamps flows into node A? What do you think is going to happen in node A? They're going to combine. And what do they combine to become? It looks like, if you do the math in your head, what, 16.5 milliamps? Does that seem reasonable? 16.5 milliamps. There you are. Makes this, do this so this is a little neater. And do this. Use a thinner draw, like so. Do this. And do this, and this. Like so. And this comes down there. Okay, does everybody see the path for how current flows in this circuit? Electrons leave the negative side of the voltage source, right here, and then flows up through R3 and up through RL2, 1.5 amps. Let me do this a little neater here as well, since I've got a fine point. 1.5 milliamps. And this is 10 milliamps. And that gives us 11.5. 11.5 add with the 5 milliamps through load 1 gives us 16.5 milliamps flowing through R1. Everybody okay with current analysis? Everything seems to make some sense here? And so why don't we now take this current analysis and fill in the information in our table. We have RL2 as being 11.5 milliamps. So 11.5 milliamps. Let me change the thickness of that pen. Okay. $11.5 milliamps. And we determined that the current through R1 was 16.5 milliamps. So are we done with current analysis? The current column is completely filled in, yes?
No.
Oh, one more. Yes, total, sorry. And so how do we determine total current? Yeah, it's going to be our 16.5 milliamps, yes? Because what flows into the source from above, the 16.5 that flows into the source from above, is going to be the total that flows right here. So 16.5 milliamps. So is our current analysis complete? Done deal. Okay. Now, how about voltages? How do I tackle V1? I don't have a resistor yet, but I have enough information to determine the voltage across R1. How do I do this?
100 minus 50.
I start with, and enlarge this, how much voltage here? 100 volts. And my first load is specified at point A as being 50 volts to ground. Is that right? So the voltage at point A, VA, from here all the way to ground there is going to be 50 volts. Because isn't point A the top of RL number 1? is at point A across or after the resistor number 1. So if I know I have 50 volts at point A, and I'm starting with 100 volts at the top, how do I determine the voltage across R1? It would be 100 minus the 50, so voltage across R1 should be what? VR1 should be 50 volts, yes? I start with 100, lose 50, I end up with 50 at point A, which supplies my RL1. Oops, don't select, deselect, okay. And how about the voltage across R2? How do I determine the voltage across R2? What is my VR2? It would be, what is the voltage at the top of R2? I have 50 volts. What is the voltage at the bottom of R2? Is 10, yes? So I have 10 volts at the bottom of R2. I have 50 volts at the top of R2. So 50 minus 10 will give you what?
40 volts.
Okay, so VR2 is going to be 40 volts. How about VR3? VR3 is the same as my load, RL2. Yes, is R3 in parallel with RL2?
Yes.
R3 in parallel with the second load resistor. So if the second load resistor is 10 volts, then VR3 must also be 10 volts, yes? So now do we have VR1, VR2, and VR3?
Yes.
So if I go back to here, VR1, we said would be $50 volts, VR2 was 40 volts, and VR3 was 10 volts. Are we good with all of that? Okay. So now, have we finished the voltage column?
Yes.
Yep. So now the only thing left to calculate is use Ohm's law to determine the resistors, yes? All right. So, oops, my thing disappeared. Oh no, come back. Not now, go away. How did that happen? I don't want this, go away. All right. So let's go ahead and determine the value of R1. So using Ohm's law, V divided by I gives you, everybody calculate that, 50 divided by 16.5 milli. Works out to be 3.03 kilo ohms. And the next one, 40 divided by 11.5. 40 divided by 11.5, what is my value of R2? Wei G?
3.48 kilo ohms.
3.48 kilo ohms. And then my voltage across R3 is 10 volts divided by 1.5 milliamps. So R3 works out to be what value, Sarah?
6.67 kilo ohms.
So 6.67 kilo ohms. And then my first load resistor is 50 volts divided by 5 milliamps. So my first load, I have to fill this in, 50 divided by 0.005. That works out to be what value, Isaac?
10 kilo ohms.
Works out to be 10 kilo ohms. And then, thank you. And then RL number 2, 10 volts divided by 10 milliamps, works out to be what, Jacqueline?
1 kilo.
1 kilo ohm. There you go. And then, let's see, Yusuf, my R total, 100 divided by 16.5 milliamps.
6.06 kilo ohms.
So 100 divided by 0.165 works out to be, what did you say, 6.06 k ohms?
Yeah.
6.06 kilo ohms. Is everybody okay with how that analysis came about? So if we can fill in a VIR table like this, can we fill in all of the blanks that were asked of us? Yeah, because I only asked you to fill in 9 blanks, but this table has a total of 18. So by completing the table, which gives you a more thorough hopefully more thorough understanding of this analysis. You're only filling in 9 cells. Hopefully you'll have some greater confidence on how to do so. Any questions about this particular fellow? Okay, ready for the next one? Okay, let me go ahead and set up the next one. So I will go ahead and do this. And okay. All right. Now let me go ahead and see if I can do it right there. Paste. Make it a little bigger so we can see it. Everybody see that okay?
Yes.
All right. So in analyzing this particular guy, where would we start? If we use the same rules we did before, what did we do before? We had to find the bleeder current through the bleeder resistor, yes? So we had to identify the bleeder resistor. The second step from above says the bleeder resistor is what? The last resistor of the voltage divider string connected to the last load to ground. If there's multiple load resistors, it's connected to the last load to ground. And then you identify which one that is. So let's look at this particular schematic. As you look at this particular schematic here, you have R1, you have R2, and you have R3. Which one of these is connected to ground? R2 and R3 are both connected to ground, yes?
Mm-hmm.
And you go, okay. Well, you get 2 resistors connected to ground, but only one of them can be the bleeder resistor. And so let's go back and look at our rules again. Bleeder resistor says it is the last resistor of the voltage divider string connected to the last load that goes to ground. So which one of these loads, because I have 2 loads here, which one of these loads goes to ground? Okay, let me go ahead and label this as RL1, and let's label this as RL2. Oops, still me. My dyslexia. RL2. I'm sorry, what's that?
On RL2, that's negative 30 volts. Right?
That's negative 30 volts with respect to ground. Correct. That's the terminology we use. It is negative 30 volts with respect to ground. So if we go back to our definitions, which one of these load resistors is physically connected to ground? Is RL1 connected to ground?
No.
Nope. Is RL2 connected to ground?
Yes.
Yep. And is there a resistor that is in parallel with it to ground?
Yes.
Yes. And which resistor is that?
R3.
Correct. We determine, oops, come on. We determine that R3 equals R bleeder due to being parallel to RL2 to ground.
So how are we supposed to have known that?
I'm sorry?
How are we supposed to have known that when we were assigned this?
Well, I mentioned it. If it would have been in the recording, or you could have asked me. And some people did. So the bleeder resistor is R3 to ground. So, and how are they both connected to ground? Let's go ahead and label these points. Let's go ahead and label this point A, label this point B, and label this point C. I have another node here. That's also point C. Does point C exist in 2 places?
Yes.
Yeah. So is the second load resistor and R3 both connected at point C?
Yes.
And are they both connected to ground? Therefore, is R3 parallel with RL number 2? R3 is in parallel with RL2. So R3 equals bleeder resistor. Now, that being said, can you determine the current of IR3? IR3 is 10% of what? Total load. Come on, Pen. Total load current. So that's equal to 10% of 25 milliamps plus 15 milliamps is equal to 40 milliamps. Is that right? That's your total load current. So 10% of 40 milliamps is going to be equal to 4 milliamps. So this is your IR3. Is everybody okay with that statement? Right there. RL3 is 4 milliamps, and that is equal to your bleeder current. Okay, so now if we go to do this, shrink this up a little bit so I can still see the circuit, and I will have a V, I, and an R. I need an R1. I need an R2. I need an R3. I need an RL1. I need an RL2. Shrink this up just a touch more. And totals. Okay, 3 columns, 6 rows, 18 cells. Where do I start? Let's go ahead and start with our givens. So Robert, give me some givens.
IR3.
IR3, okay, IR3. We just determined IR3 was 4 milliamps. Well, that was a calculation, wasn't given, it was our first calculation. What's given? Robert? Do I have the current for RL1?
Yes.
And that is?
25 million.
So 25 milliamps. Do I have the current for RL2?
15 million.
15 milliamps. What else is given?
80 volts.
80 volt source. This is my 80 volt source. And what else is given? Load voltages. So RL1 is how much voltage? 40 volts. RL2 is? It's 30 volts. And you'll see why it's negative, but why we only write down 30 volts in our table. Let's go ahead and polarize everything so you can see how currents flow in this particular circuit and why it comes out looking negative. Is there anything else that's given? Nothing else is given, eh? We filled in all the givens plus our bleeder current. All right, so let's go ahead and analyze how currents are flowing in this particular circuit. Okay, let me change the pen tip. Let's go ahead and start by polarizing this schematic. So if I go to polarize this schematic, I have positive on the top and negative on the bottom of my 80 volt source, correct? This side, the left side of R1 right here has what polarity, Sarah? The left side of R1.
Looks like R1 is positive.
And it's positive because it is attached to the positive side of the voltage source. Is that correct? Everybody see that that side should be positive?
Yes.
Okay. Which means the other side of R1 is negative, yes?
Yes.
Good deal. Now, electrons will flow which way? Electrons will flow down from the source. Electrons will flow back to the source from the top. Did I draw the arrows for electron current correctly for the left side of that circuit? The electrons will flow here, here, and into node C. What happens at node C? The current will split. Which way will it flow through R3? It will flow up through R3, correct? Which way will it flow from point C to point C? To the right. So far, so good? What happens at the second point C on the right-hand side of the circuit? It splits. So part of the current through the RL2 goes in which direction?
Down.
Yeah, so part of the current comes down and down to ground. What happens to the current at node B? The current that went up through R3. At node B, what happens? It splits also. Part of it continues to go up, part of it goes to ground. So far, so good? Okay. Then,
That the current flows toward A and not from A to B.
I'm sorry. Why doesn't it flow from A to B?
Yeah, how do we know it's going in that direction?
No, because right here, if you take a look at the left side of the source, the left side of the source, the bottom of the source, the 80 volts, isn't that a negative polarity right here?
Mm-hmm.
Which means the bottom of R3 is negative, yes?
Yep.
And it also means that the top of R3 is positive, correct?
Yep.
And we know electron must flow from negative to positive, is that correct?
Yep.
So it's got to flow up. Once it hits the node B, then the current will flow up. If you take a look at this side of R2 will be negative, this side of R1 will be positive, because the current, once it hits node A, must continue through R1 to the left. And through this loop, through this larger loop right here, the current is flowing through this loop. Hard to point on my screen, but through this loop on the left-hand side, the current is flowing counterclockwise. All right? And then through over here, what will happen is this current will also flow up this way because it splits. Part of it goes down through here, and then the other part comes up through here and up in that direction. So what will happen is actually, we have a return path. Let me correct something here. Take this guy out. This is a return path because the current through the second load resistor goes down, yes? Right here. And it goes to ground and it comes back up from ground and contributes right there. The current here goes up, 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 and over to the right in this direction. There's your complete current. So the direction of this guy should be coming up from ground back to here. Goes down to ground on this side and comes back up from ground like that. Okay? And let's go ahead and look at the polarities and why this guy works this way. Electron current, now this is a reminder. Electron current flows from negative, let me write that a little better, flows from negative side of a device, comma, through it, comma, to the positive side of that device. And so all of our polarities are defined on that basis. Take a look at R1. We said that the current returns to the source going to the left, yes? Does it in fact flow from the negative side of R1 through it to end up coming out the positive side of R1? Okay. Take a look at R3. R3 is negative on the bottom of R3. Why? Because it is physically attached to the negative side of the voltage source, yes? So the bottom of R3 is negative. It's physically attached to the negative side of the source, which means the top of R3 is positive. And doesn't the current, electron current, flow from the negative side up through it to the positive side of R3? So is the direction of current through R3 going up? Take a look at R2. R2 has current flowing up through it because it combines with the second load current. And the second load current is 15 milliamps right here. And we have 15 milliamps combining with the 1.5 milliamps for the bleeder current. If these two currents combine, I have 1.5 milliamps flowing here. I have 15 milliamps flowing here because 15 milliamps comes from the second load. What happens in node B with these two currents? They combine. So what will 1.5 and 15 milliamps combine to become going through R2? 16.5 milliamps. Yes. So we will have 16.5 milliamps going up through R2. Now, do I know the current coming from the first load? The current coming from the first load is specified as what? 25 milliamps, yes? So I have 25 milliamps.
How do we get 1.5?
Yeah.
Yeah, shouldn't that be 4?
Oh, yeah, we have the wrong.
Oh, I'm sorry. Yep. Thank you.
Great.
Catch me earlier. 4 milliamps. So that will make this right here, 19 milliamps, yes? There we go. Thank you. So 19 milliamps. So we have 19 milliamps coming up through R2, and we have 25 milliamps coming in through the first load. So these two must combine, give you current going through R1. What do they combine to become through R1? Is that 44 milliamps? Okay. 44 milliamps. And if 44 milliamps is going back into 44 milliamps, is going back into the source, how much comes out of the source at the bottom? 44 milliamps, because what comes out of the source has to equal what goes into the source. And let's see if the math works out. So 44 milliamps, and 44 milliamps is here, 44 milliamps, flows into node C. We said how much current flows up through R3? How much current flows of the 44 milliamps coming into node C? 4 milliamps goes this way. What happens to the rest of the current? It goes between this node C and this node C through this wire, yes? How much current is on this wire? 44 milliamps minus 4 gives you 40 milliamps. That wasn't asked of you, but you can determine that. You have 40 milliamps going in this direction. And of that 40 milliamps, does it split at node C such that you have 25 milliamps going that way and 15 milliamps coming this way? So does the math for our currents work out? 40 milliamps coming into this node C, 25 milliamps going up, 15 milliamps coming down. There's your 40 milliamp split. Okay, so far so good. Now, here's how you look at that negative voltage. Watch this. So the bottom of the first load resistor should be what polarity? The bottom of this first load resistor, RL1.
Oh,
What polarity at the bottom of RL1?
negative.
Should be negative. Why? Because that was the reminder. The reminder tells you electron current flows from what side? Negative side of the device through it to the positive side. So the bottom's got to be negative and the top's got to be positive. Now, take a look at RL2. Which way is the current flowing through RL2? Up or down? Down. Which means that the top of RL2 should be what polarity?
Negative.
Negative. And the bottom of RL2 should be positive. So when you go to use a digital multimeter and you hook up the red lead here and the black lead here, we will see the 30 volts, but we will see what polarity on that 30 volts? Negative. That's what your digital multimeter will show, because it's seeing the negative polarity based on how current flows in this particular circuit. Okay? All right. So have we drawn all the currents and determined all the numbers so far?
Yes.
Okay, I'll fill this in. 25 milliamps goes that way, and 15 milliamps goes that way. Cool. All right, I think we have it all. So based on that, let's go ahead, take that information and fill it in our chart, fill it in our table. So RL1, we said, would be 44 milliamps, yes? RL2 should be what, 19 milliamps? And R3, we said, was the bleeder resistor, so that's 4 milliamps. Okay, and then the total current, 44 milliamps. Have we completed our current analysis to fill in this table so far? All the currents are determined, the directions of currents are determined, and the math seems to work out. Everybody okay? And the polarities should also work out. Now, how do you determine the voltage of R1? How do we determine the voltage of R1? We have on this node, right here, I'm going to draw a node, and let's go ahead and label this X. So voltage at X is equal to 80 volts. Is that correct? That's the top of the voltage source. Do I have voltage at point A? How much voltage is going to be at point A to ground? Well, we don't know how much to ground yet. We'll leave that one alone for just a moment. Do we know how much voltage? Yeah, we do this. Let's go ahead and take a look at RL2. So RL2, is RL2 connected at point C to ground?
Yes.
Is R3 connected at point C also to ground?
Yes.
Is RL2 in parallel with R3?
Yes.
Because that's the bleeder resistor has got to be parallel with the last load resistor. So do I know the voltage here is given as 30 volts from this point to ground? Do I know the voltage across R3?
Yes.
Also 30 volts, because why? They're in parallel with each other, yes? So the voltage across R3 is 30 volts. Is everybody okay with that?
Yes.
Because of the parallel relationship. So my VR3 right here, VR3 is equal to 30 volts. So I got a question for you. If I ask you for VC, right here, put the V in front of the C. If I ask you for the voltage from C to ground, look at my drawing. If I ask you the voltage from C to ground, what is it? It's a negative 30 volts. If I ask you the voltage from C, because this is C here also, C to ground, the red probe at point C sees what polarity? Also negative 30 volts to ground at point C. If I ask you, however, for a voltage across a resistor, is there any implied position for red and black probes? No, I'm only looking for a magnitude. So this is a 30 volts between here and here, and that's what you fill in on your table. You don't write negative 30 volts on your VIR table. Are we clear on that? Okay. 30 volts would be negative only at a point with respect to ground. And it is negative 30 volts from here to here, and it's also negative 30 volts from here to here. But for any voltage across a resistor, just a VR, there's no specification where the red probe goes, where the black probe goes. We're only looking for the magnitude of voltage, the difference of potential across this resistor, and that magnitude is 30 volts. And so, on that basis, we will go ahead. My VC right here is equal to negative 30 volts, but my VR3 is just simply 30 volts. So that will allow me to put in this value right here, 30 volts. How do I determine voltage VR2? What can I do to determine my VR2?
Should be 30 plus 30, right?
VR2. Well, here's the thing. Now I'm going to have to use two hands for two probes. This is my red probe. Imagine, this is my red probe. My black probe. Do I have a load, RL1, that says it requires how many volts?
40 volts.
That means from here to here is 40 volts. Is that correct?
Yes.
Is this red probe attached to point A?
Yes.
Is my black probe attached to from point C to point C?
Yes.
So between these two probes, I have to have 40 volts for this load resistor, yes?
Yes.
Between these two probes, I have 40 volts across these two resistors.
Okay.
Aha. I have 40 volts between these two probes. Do I know one of the voltages of the resistors?
Yes.
But I have 40 across both of them. So how do I determine this missing voltage up here?
40 minus 30.
40 minus 30, is that correct?
Yes.
That tells you your VR2 must be 10 volts. VR2 must be 10 volts. So VR2, oops, come back here. 10 volts. How do I determine VR1? Is it 80 minus 40? Is that what Kirchhoff says in any closed loop? In any closed loop, do I have a closed loop right here?
Yes.
Yeah, in any closed loop, the algebraic sum must add up to be what?
0 volts.
Algebraic sum is 0. Or in any closed loop, the voltage drops have to add up to the voltage source.
Yes.
That's another way of looking at Kirchhoff's voltage law. So I have 80 volts in this loop. I have 3 resistors in that loop. 80 volts minus the 30 minus the 10 gives you what's left over across R1.
40 volts.
40 volts. That's one way of looking at it. Another way of looking at it is, don't I have at point X 80 volts to ground? Or 80 volts. From here to here, I have 80 volts, yes?
Yes.
So I have 80 volts here. Do I have potential at A? My potential at A is 40. So if I have 80 over here and I have 40 over here, what is my difference across R1? 80 minus 40 is also 40. So VR1 is equal to 40 volts. Does that complete my voltage column?
Yes.
So we start off with current analysis. The currents allow us to mark polarities because the current arrows tells you what direction the current flows and what polarities are found where. And then we find out our voltages. The only thing left is Ohm's law to determine your resistor values, yes? All right, so it's just V divided by I. So The value of R1 is 40 divided by 44 milliamps. Isaac, do you have that number for us, please? 909.09 ohms, omegas, right there. Good, thank you. And then R2, 10 volts divided by 19 milliamps, Wei Ji.
526.32 ohms.
526.32 ohms. And VR3 is 30 volts divided by 4 milliamps. Sarah, do you happen to have that for us? Okay, yeah, 30 divided by 0.004.
7.5 kilo ohms.
7.5 kilo ohms. Terrific. And then RL number 1, 40 divided by 25 milliamps, Jacqueline?
1.6 kilo ohms.
1.6 kilo ohms. And RL2, Robert, 30 divided by 15 milliamps gives you 2 kilo ohms. And Yusuf, the R total, 80 divided by 44 milliamps works out to be
1.82 kilo ohms.
1.82 kilo ohms. That's the last column we fill in. Okay. Is everybody all right with the voltage divider analysis for the upper voltage divider as well as the lower voltage divider? Any questions? Was it number 1, number 2, or number 3?
Number 2?
Number 2?
No.
Number 2 has 1 IT, but there's voltages. Okay, number 2. Let's go ahead and talk about number 2. That's a good one. I think would be good for us to review. Let me go ahead and do this. That's impossible to try to find that one. So close that one, minimize this, go here. And let me just put this up on the board over here for you. Actually, I'd like to record it. So let me see if I can get it again. Here. Yeah, take a look at number 2 on the take-home test number 2. And some of you had some challenges on the second branch. The third circuit, most people were able to get just fine. But the second circuits, there were some challenges. So let me help you through that. When this can stabilize, and it will in a moment. So VR1 works out to be what value for the second circuit? Jackie?
You said that I got it wrong. I should not be answering this.
Oh, okay. All right. Let me go ahead and pull that up now that it's available for us. So, test number 2. And open up test number 2 or download it. Here comes Word. Not now for feedback. Can't move this guy up. And let me go ahead and capture that circuit. New. This one right here. Okay, and copy. Now let's go ahead and paste this right there. Cool, make this bigger. Okay, everybody see the circuit okay?
Yes.
All right. Let me go ahead and share this screen. Find here and share. And this screen. And I want to resume our recording. All right, so if we take a look at this, you're given one very critical piece of information in here, yep? The critical piece of information, helps if I use the right pen, thank you. The critical piece of information that you are given is right here. You're given IR2 has a certain value. So you're given IR2 is given 200 microamps, yes? So I'm going to arbitrarily draw a direction of current, and that's 200 microamps. So far, so good? All right, I have 4 resistors, so let's go ahead and set up something simple. So let's do a V, I, and an R. I'm going to do this for 4 resistors. So I have an R1, have an R2, R3, R4, and total. Everybody see that all right? All right, let's go ahead and put in my columns there and there. So let's go ahead and fill in our known quantities, yeah? R1 happens to be 2.2 kilo ohms. R2 is 1 kilo ohm. R3 is 3.6 kilo ohms. R4 is 1.5 kilo ohms. So far, so good? Okay. Now, something else that would help us along quite a bit. Let me move this little fringe window out of the way. Move this guy off our screen. Take the keyboard away. I need to draw us a redraw. And this redraw will look like this. I have a here. Could I redraw the 4 resistors down to 2 resistors like this?
Yes.
Okay, so my upper branch is a combination of R1 plus R2, yes? So I could label my REQ1 as being the sum of 2.2 plus 1K, which is 3.2 K ohms, is that right? 3.2 kilo ohms. And then my REQ number two is equal to the sum of 1.5 and 3.6 K ohms, so that should give me 5.1 kilo ohms, is that right? 5.1 kilo ohms. So my R total is equal to REQ1, horrible one, REQ number 1 in parallel with REQ number 2. Can you do that, please? Can you put these 2 in parallel with each other? And if you do, it should calculate to be an RT. That's a 1.97, yes? 1.97 K ohms. Is everybody okay with that? So far, so good? Okay, so our R column is determined. Nothing else left to do for our R column. So far, so good? Any questions there? All right, let's go ahead and analyze our currents best as we can. So you are given 200 microamps going through R2. 200 microamps, oops, wrong place. 200 microamps going through R2. What else do we know based on that current in that upper branch? What else do we know? Do we know the current that goes through here? It's got to be the same current because isn't R1 and R2 in series with each other? So it's got to be the same current. It's got to be 200 microamps here as well, yes? One current path, so R1's got to be 200 microamps. And here's where some people had a challenge. Some people use that 200 microamps on the second branch. Do we know should it be 200 microamps on the lower branch? Nothing says it should be. There's no aspect of the problem that states that you have 200 microamps on the lower branch. What do you know? Let's take this. Do we know the current that flows through this upper branch? And isn't that 200 microamps right there? Yes? Well, take a look at my redraw. My redraw has 200 microamps, and I have 3.2 k ohms. Do I have enough information to determine a voltage across REQ number 1? How do I determine the voltage across REQ number 1? Don't I have current and don't I have ohms? Can I multiply the two together? If I multiply the two together, won't I get the voltage across both of these, this EQ number 1? What do I end up with? So it works out to be 640 millivolts. Is that right or wrong?
Right.
Okay. That's 640 millivolts, and I'm going to label this point A. I'm going to label this point B. Everybody see where I mark point A and point B? So if I have 640 millivolts based on Ohm's law up here between point A and point B, don't I also have 640 millivolts across REQ number 2? Is that right? That's 640 millivolts across the first branch is the same as the voltage across the second branch. So I now have a voltage across 5.1 k ohms. If I now have a voltage of this across 5.1 k ohms, can you calculate a current?
Yes.
Please calculate that current. Those are the keys to the kingdom right there. This is also 640 millivolts, which means the current flowing through here must be, this is I, R, E, Q number 2, must be equal to 640 millivolts over 5.1 kilo ohms. So this calculates to be how much current do you calculate, Yusuf?
125.5 microamps.
125.49 microamps. So 125.49 microamps. How many people agree? Okay, so far so good. Do you now know, because that's based on Ohm's law, do you now know the individual current flowing through R3 and flowing through R4? Can I fill them in my table? 125.49 microamps, 125.49 microamps. There we go. So far so good. So how do I determine my total current? I have 200 microamps flowing in from the top, right here. I have how much current flowing in from the bottom? 125.49 microamps flowing in from the bottom. What is happening at node B when these two currents come together? Don't these currents add to give you a total current coming out? So what is my total current coming out? 325.49 microamps. Is that correct?
Yes.
Yay? Okay. And then calculating the voltage is academic. Just Ohm's law. Everybody okay with that? Let's go ahead. Let's write down what those voltages are for the benefit of our classmates. So VR1, take a look at VR1. do I have current? Do I have current through here of 125/40, excuse me, VR1? Do I have current of 200 microamps? Do I have ohms? Can I calculate a voltage here? I have the same current through 1K ohm. I can calculate a voltage here. So the voltage for VR1, Sarah, what do you have?
440 millivolts.
We have 440, all right, do this better, 440 millivolts. And WG, the voltage across R2?
200 millivolts.
200 millivolts. And if you look at the lower branch, do I have a current through the lower branch of 125.49 microamps? Isn't this current flowing through R3 and flowing through R4?
Yeah.
So could I use this current times these ohms for a voltage? Use this current times these ohms for a voltage. So my VR3, Isaac, do you have my VR3?
And 451.76 millivolts.
So 451.76 millivolts, correct? And my VR4, let's see, Robert, do you have VR4?
188.25, or sorry, 0.24 millivolts.
188.24 millivolts. Is everybody okay with each of those four voltages?
Yeah.
Now we just have a total. How on earth do I find the total? Well, I have total current, yes? I have total ohms, yes? Ohm's law, same way. And so the voltage total works out to be what, Yusuf?
41.22 millivolts.
Yeah, if we add up the first two, simply 640 millivolts. Okay. Okay. Any questions on that? So far, so good? Okay. All right, I think that was probably the more challenging one on that page. And then the last one, let's go ahead and, does everybody have all the numbers they need off of this? Because I'm going to go off the screen. Stop the share. Stop the share. Okay, do you have your IDE up on your computer screen? If not, I'll show you where the Arduino program is set on our, right there. All right, so as we walk through the code, let me point out a few things for you. Some things are comments. They're simply notes to the user. So a slash and a star is a beginning line of your program here. This is a double slash, this is a comment. So anything that follows the double slash is just information for you. So this is where your programming has a note here. So this is blink. What does blink do? This is one way of doing a comment. A slash with a star, it creates a comment section. So slash with a star begins a comment session, and a star with a slash closes the comment session. So all of this is just for the user. It tells you, the user, or somebody looking at your program, what the purpose of the program is. So the program is called what? Blink. And that's the name it's here. What is the purpose of blink? It does what? Turns on an LED, on for 1 second, then off for 1 second, and continues how? Repeatedly. So none of this comment does the Arduino board ever see. It's for humans, so that whoever reads your code can see the name of the code. And typically when you go to type this out, it'll be blink by Sarah, or blink by Jacqueline, or blink by Weiji, or blink by whoever. You normally put your name right in here. In the comment on the first line after the name of your particular program. So how do we start a comment line? One way to start a comment line is a slash with a what? Yeah, a little star. And how do we end a line or several lines of comments would be star slash. Okay, now, some additional things here. A double slash is another way to do a comment. The setup function runs how many times? Once. When you press reset or power the board, and then you have some things that are happening in here. Double slash, initialize digital pin 1, a digital pin LED built in as an output, and then this tells us what's going on here. Then you have another double slash, loop function runs over and over again forever. So here's actual programming. The double slash shows a comment, a single line comment. This double slash and anything that follows here, Arduino doesn't care about. It's for humans. Again, it's a prompt that tells whoever's reading your code, what does it do? The setup function runs once when you press this reset or power on the board. Now, this is an actual line of program code. So void setup, open, close parentheses, and then you have this. And then another comment here, initialize digital input pin. That's again for humans, but this is a program code line right here. And so the program begins at this open brace and a close brace right here. So whatever between here and here, that's not a comment, is code. This particular chunk of code happens between here and here. Then you have another comment. The loop function runs over and over again forever. Void loop, and this is the beginning of code. This is the end of code, and you have 4 lines of code. Digital write, LED built-in high, close, and then this is comment. What does this line of code do? It turns on the LED. High is the voltage level, because it says high, and then delay 1000. This is in milliseconds. So 1000 milliseconds would be 1 second. If I wanted 2 seconds, what would this number be?
2,000.
2000. Wanted 3 seconds, this would be.
3,000.
If I wanted half a second, what would it be?
500.
500. So you can change the time by changing the delay number, the delay variable right here. So this says wait for what? 1 second before executing the next code. The next line of code says digital write to the board, LED built in, will be low, meaning over here, a comment line, turn the LED off by making the voltage on low. And then again, delay for how long? 1000, wait for a second, and then do this. So what I'd like for you to do is on your IDE screen, let's go ahead and we don't have to copy everything because we don't have time to do that, but we can just copy the code. So let's go ahead.
You want us to delete everything that's on this one?
Yeah, delete what you have there because we're going to start from scratch. So I'm going to move this over to one side where we can see it. Or I can see it. You have your booklets. And now let me make sure I'm sharing the right screen. So share screen, and I want the Arduino screen. So that's now set up on our Zoom. Okay, so I'm going to skip all the comments. The very first thing is void setup, open parentheses, yes? And then the next chunk of programming will be pin mode. So I'm going to take all of this and where's my keyboard? Now I need my keyboard. Let's raise this back up. Delete. Okay, so my next will be pin mode, P-I-N, capital M-O-D-E, open parentheses, LED underscore built in, comma, space, output. And close parentheses, come back here, close parentheses, output, close parentheses, and let's put in So do we have void set up, open and close parentheses, and open a brace? Then the second line would be pin mode, open parentheses, capital LED underscore built-in, comma, space, output, close parentheses, and we have a semicolon there. Then on the third line, I'm going to close brace. Does that match what you have in your book so far? Okay, all right, then let's continue. Enter. So on line 4, again, we're going to skip the comments and go to void loop. So VOID, loop void, space LOOP, void loop, open and close parentheses, space, open brace. Next line. Digital, right, open parentheses, LED, underscore, built-in, comma, high, close parentheses, put a semicolon there, enter. Next will be delay. And I'm going to ask you to change something. Actually, let's just use program code. Just type in 1000. 1000. And then digital write. Open parentheses. LED underscore built in. Comma. Low. Close parentheses, like that, and then we have another delay, DLAY, open, 1000, close, and there. Okay, so you should have 9 lines of code, yes? Okay, so I'm going to use the upload button, which is the arrow to the right. Save sketch. Find a suitable place to save this. Arduino, sure. Sketch, November 30th. Go ahead, save. It's got a date on here. Yes. Did it upload?
I just got an error.
Oh, okay, let's check. Let's see what the error shows. It's one of the typos. Oh, you got it.